now friends, after understanding what sets are, the Venn diagrams and improper and proper sets, right now let's learn different types of sets, different kinds of sets that we have. The very first and the most simple thing is called the null set, right? Now, null set, as the word itself suggests, and I think we have done an example before this as well, a null set is something which has zero elements in it. So basically a condition which does not give you any element will be a condition which will give you a null set, and it is generally represented as such for obvious reasons, because there are no elements inside the two braces, there will be nothing. And generally it is also represented by this symbol, which we call as the phi symbol, but here it represents a null set. So null set, and we can represent it in the roster form like this with the braces, no elements inside it. Now let's see a couple of examples which basically are null sets. Now a particular set of odd natural numbers divisible by 2. Will this be a null set? Let's try and figure out. Now, let's pick up any odd number, odd natural number to be specific. Let's say 7. Is that number divisible by 2? No. And for that matter, any odd natural number you pick up won't be divisible by 2, because that is how the basic definition of an odd number is. An even number is always divisible by 2, and an odd number is always one more than an even number or one less than an even number. So it will be always not divisible by 2, and hence the set of odd natural numbers which are divisible by 2 is a null set, because there won't be any element which is an odd number and at the same time divisible by 2. Now on the other hand, if we think of a set which is let's say a set of prime numbers which are even numbers as well, right? Do you think this is a null set? Because we know prime numbers are mostly odd. All the prime numbers are odd except for one prime number, which is 2. So 2 is a prime number which is not odd, so basically it is an even number but is still a prime number, right? So the set of even prime numbers is not a null set, because there is one element inside that, and this kind of a set is called a singleton set. So basically any set which has a lone element in it, only lone member in it, that is called a singleton set. So here goes the second type of set, as we call it the singleton set. Only one element, and there can be many examples to this. One of them, as I said, even prime numbers. There will be only one element, which is 2, and hence a singleton set, only one element inside it. Now after understanding a null set and singleton set, let's move further to another kind of classification of sets, and this time we are going to learn finite and infinite sets. A very simple thing to understand by its name itself. Till now we have learned many different kinds of sets, and most of them were finite sets, as the word itself suggests. Finite set is a set which has finite elements in it. We can find out the number of elements in that set. So a finite set, clearly having finite elements. We can find out the number of elements in it. And on this note, I'd like to introduce another terminology, that the number of elements in a particular set, number of elements, is also called the cardinality of that set. So basically, cardinality is nothing but the number of elements in a set, as we have represented that as n of that particular set. Let's say the set is S, then n of S is nothing but the number of elements of that set, which is also called the cardinality of that set. And if we can find out the cardinality of a particular set, or if we know that the number of elements or the cardinality of a particular set is finite, it is called a finite set. And obviously, on the other hand, if we have infinite elements, then it becomes an infinite set. We have definitely seen n number of examples of finite sets. Let's see a few examples of infinite set, right? Now, infinite set, one example can be a very simple, the most simple example can be this. Now, as you can see, this is in the set builder form, and it says that every element x, where x is a real number. If x is a real number, then it is an infinite element, because as we know, there are infinite real numbers on the number line. So this becomes a particular set which is an infinite set. Likewise, if I say that the set of odd natural numbers, even that is an infinite set. And this time let's try to write it in the roster form. The set of odd natural numbers, as you can see. Now, these dots here represent that this list is endless, and when this list is endless, it clearly suggests that the set is an infinite one. So these are a couple of examples of infinite sets, and as we know that there are many examples that we have seen about the finite sets. Next on our list is equal sets and equivalent sets. Let's understand these two terminologies. Equal sets and equivalent sets sound similar but slightly different in their definition. Equal sets, as the word itself suggests, is basically two sets which have absolutely same elements in them. So as we have seen in the first slide, the set of all vowels in the English alphabets were represented in two different forms. The first type we saw basically the set builder form itself. So as we saw in the roster form, we had two different types. The first one was A, E, I, O, U, and the second one we had basically flipped and flopped the elements and kept the elements same. The number of elements were also same, rather the elements were also same, just the order was varied. So these two sets would be equal sets. So let me have that same example again. This is absolutely equal to this, because as we can see, this set has these elements and this set has the same 5 elements as here, just the order is changed. So these two will be called as equal sets. Another example can be this. Right, again the order has been changed. I can again write 1, 2, 3 again, but it will be the same set. Basically, equal sets is nothing but two sets which have the same element. Now, when we talk about equivalent sets, this is slightly different, right? Now, on the other hand, there is one thing I would like to talk about equal sets as well. Now, I can also write 1, 3, 2, 2, 3. This would still be equal to these two. The reason behind that is here, as we know that in roster form we cannot repeat elements, but these elements are repeated here. So these two elements don't have any significance, right? And hence this set has these 3 elements which were the elements of the original set. So even this can be called as an equal set to these two, right? Now coming to equivalent sets, the condition is the number of elements have to be same. The elements does not matter what the elements are, but the number of elements should be same. So let's take an example. Now if we take 1, 2, 3, or for that matter, let's take 3, 1, 2, it's one and the same thing, right? 1, 2, 3 and 3, 1, 2 is one and the same thing. These two are equal sets. But this is an equivalent set to, let's say, A, B, C. Right? Because the cardinality of both these sets is same, is 3. So for example, I can have January, March and December. Even this will be an equivalent set to these two. because as we can see, the cardinality is same on both the sides. Now, after understanding this, let's move further to the next classification. Rather, this is not a classification but more of a property, and this is called a universal set. As we have learned when we understood the Venn diagram, universal set, as the word suggests, is basically the universal collection of all the elements involved in a particular situation, right? So now let's understand this by taking an example rather than the Venn diagram. Let's say we have a set A which is 1, 2 and 3. Then let's say we have a set B which is 3, 4 and 5. Now let's say we have a set C which is 7, 8 and 9, right? Now if I try and find out the universal set to all these three, right, the universal set would be generally represented by U, and that is going to be 1, 2, 3, 4, 5, 7, 8 and 9. Now as you can see that here we have 8 elements, here we had 9 elements, because there is one element which is repeating in these two sets, which is 3, and hence we have taken that only once, and that is why the cardinality of U is 1 less than the addition of the original 3 sets. So basically a universal set is simply a collection of all the elements of which universal set is being processed. So this is how we figure out a universal set, and generally in the Venn diagram we represent it with a rectangle. So inside the rectangle we have different small circles. So for this particular situation, this is how we would represent the universal set. We have a set A, as you can see, we have a set B and we have a set C over here. A will have 1, 2 and 3, B will have 3, 4 and 5, and C will have 7, 8 and 9. Now as you can see, A and B, these two sets have one common element in them, but A and C, and at the same time B and C, these two sets, these two combination of sets don't have anything in common, and that is why the new thing that comes up here is the disjoint sets and intersection of sets. So from this particular figure, let's try and understand what is disjoint sets. So disjoint sets is basically no element in common. So basically A and C in this diagram are disjoint sets because there is nothing in common between them, and at the same time B and C is also a disjoint sets. Basically these two even are disjoint sets, a pair of disjoint sets as we can call it. So we'll write A and C, B and C, these two are pairs of disjoint sets. Now, as I said, A and B, these two sets have one thing in common, and that is why A and B will be called as intersecting sets. Now later in the next slide we'll be learning about union of sets and intersection of sets, where we will see how the intersecting sets can be represented in an algebraic way. How can we write basically intersection of two sets? It is written in this way: A intersection B. This is the general symbol for intersection, although this is the symbol for union, which we are going to learn in the next slide. No need to worry about that. So here we understood what disjoint and intersecting sets are from this diagram. Now let's learn something more interesting, which will be the complementary set. So now for understanding complementary set, let's take a new set of numbers. Now here we have numbers ranging from 1 to 9. This particular rectangle, this particular universal sets has all the natural numbers less than 10. As you can see, we have 1, 2, 3, 4, 5, 6, 7, 8 and 9, right? We have these 9 numbers in this universal set. Now there is a set inside this which is a set of odd natural numbers less than 10. So basically what I'm talking about is 1, 3, 5, 7 and 9. So let that be defined by that set A, 1, 3, 5, 7, 9. This is, I have written in the roster form. I can write it in the set builder form as well. I can write this as A is equal to X. X is an odd natural number and X is less than 10, right? So this is how I can write it in the set builder form. But now in the Venn diagram, as you can see, A is basically a circle which has all these 5 numbers, 1, 3, 5, 7 and 9. Now talking about what a complementary set is. A complementary set is basically the set which is formed by the elements outside the set A but in the universal set U. So we write A dash as the complementary set. This is how the symbol works, and that will be nothing but the universal set minus A. So here subtraction doesn't work as the normal algebraic subtraction that we have, but here the subtraction means that have all the elements of U, subtract or basically eliminate, remove those elements from A, you will get the complementary set of A. Now as you can see in the Venn diagram itself, if I remove 1, 3, 5, 7 and 9 from this universal set, what I get is 2, 4, 6 and 8. So A dash will be 2, 4, 6 and 8. So this is the complementary set of set A. The simple definition as it goes, all the new set which is formed by the elements outside the set A in the universal set U. So this is another thing that we learned in this section. We learned different kinds of sets that we have, starting from null set, a singleton set, finite infinite sets, equal sets, equivalent sets. Then we learned about universal set. We learned it through a Venn diagram as well. We understood what disjoint sets are, what intersecting sets are, and finally we learned about complementary sets. In the next slide, my friends, we'll learn a few more things. De Morgan's principle we are going to learn about, as I said, intersection of two sets, union of two sets, how to find them out diagrammatically, basically using the Venn diagrams and all. See you in the next slide.